Welcome, everyone. The purpose of this hour, the first of our two for today, is to review what's going to be on the midterm on Monday. So the midterm is Monday morning at 8 a.m. and in SEC 205 upstairs. We've not been in the classroom yet, so it's going to be kind of new for everybody. And I hope it's unlocked, number one. And number two, I hope we don't have squatters in there. So I'm going to try to get there extra early, but we're pretty good at dealing with all kinds of situations, as you guys have proven for the last 2 weeks with all of the schedule complications that you've tolerated. And so nothing can happen that'll keep us from being successful in this. So I want to walk through this. There's a version of this out on the Google Drive under exam prep. So I'll possibly edit it if I go through here and see I need more detail, but one of the things that we need to make sure you understand is on Monday, I'm going to make everybody spread out if we've got room for it. We may not in that classroom. You'll need to bring a calculator. You will need a calculator, and if you want to use the one on your phone, that's okay. We don't use blue books. We don't use Scantrons. You also can bring a single sheet of paper, double-sided, with whatever notes you want on it. But it's very important that before you go to bed on Sunday or when you get up on Monday, make sure you print this study guide, because if I revise it and I add some images or equations to it, that is because they will not be on the exam again. So if there's also an equation or table that you need, go ahead and jot it down on your cheat sheet if you like. So there are, I want to say, like 3 or 4 helpful numbered items here, and then some sample problems. So we basically are going to spend some time going through that. We may not take the whole hour. And then I'm also going to go over a couple of the problems on homework 5 that's due tonight that several of you have been asking about, and it looks like people might be struggling on one of them a little bit. So we're going to make sure everybody's clear on that. And if I feel good about it, I may add a problem based on that on the exam. But let's just get going in here. Remember the 5 layers of the protocol stack, right? Application, transport, this is where UDP and TCP live. You've got network, data link, and physical. And I have a really handy table that I could not find before I printed this out a minute ago that lists this. It lists what the name of the type of address is, whether it's process ID, port number, IP address, Ethernet address, et cetera. It lists the kinds of devices that you find at each layer. It lists some of the more popular protocols in each layer. So it's a nice grid, and I will add that. So give me a chance to throw that in there and put them up. So the reason I tell you to print this off on Sunday evening or Monday morning is because I will likely revise it. So if you are going to make notes, don't make them on this yet. Make them on your own cheat sheet. So if I change this, you're not going to have to redo all of your notes again. Assume programs run at the application layer unless you know otherwise. Remember, routers go to layer 3, switches go to layer 2. However, when you connect to a device and it is the device you are talking to, not asking it to provide a service like passing things through for you, but if you're actually trying to terminate a protocol and communicate, exchanging messages back and forth with that device, like logging into it, pulling up its configuration web page, sending it a simple network management protocol message, then the layers may usually be up at the application layer. So just because a router always runs at layer 3 doesn't mean it can't run the rest of the layers. Just because the switch runs at layer 2 doesn't mean it can't run the rest of the layers. Think about it. If you're a network administrator and you want to be able to log into this device and change its configuration, you may want to do that with Telnet, just a terminal window. And you do not want to have to get in your car and drive out there to do it. So Telnet is an application layer protocol. The only way in the world you're going to be able to Telnet to this thing is if it has a little Telnet server running at layer 5. No one else ever sees it unless they try to tell them to it. Most of the rest of the time, the switch is just moving things around at layer 2. Same thing with the router. If a router has a little status page that you can go to that's buried behind a little web server because everybody's got a browser handy, and you go there and you have to put your username and password in the URL as well, something like that, and you get like a page of status information. Well, that web server is running on the router at layer 5, right? So just because everybody else goes through the router and they never cause any software to be accessed that is running anything above layer 3 because all of the routing and forwarding happens there, it doesn't mean that device can't run higher layers. And the last example I'll give you is when new routing code is written, it's written in a test environment. And that test environment is similar to one that you might use to program an Arduino or a Raspberry Pi or a BeagleBoard or a TinyDuino or something like that if you've done any Internet of Things kind of programming or if you took architecture. That environment simulates, in the case of a router environment, you're trying to figure out how your new router code will work on a real router. So that runs at layer 3, but of course you're on a PC with Windows, and that's running all the way to layer 5. So don't get fooled by that, by the normal job that it does and what it's capable of doing. Okay, remember the 4 types of delay: processing, queuing, transmission, and propagation. Processing and queuing happen inside the routers. Transmission delay is how long it takes from the time you begin sending bits onto the wire for a second to elapse. And that's the bandwidth. And if you continue on until your entire packet is sent, that's your particular transmission delay. So if I have a 10 million bit per second circuit, it simply means that it doesn't tell me anything at all about the complete story for how long it's going to take to get to the other end, because the other 3 delays play a role in that. All it tells me is if I give it 1 bit and tell it, please encode this in your signal on the wire, it'll be ready for the next one in 1/10 millionth of a second. So I can send 10 million bits in 1 second. If my packet is 500 bytes, then it's 40,000 bits. It's going to take a fraction of that. So that's transmission delay. And if you think about it like a stack and how fast can you push stuff onto the railroad as it's going by, maybe that's a helpful analogy. Propagation refers to how long it takes to get things across the network. I don't know if this is correct. This is probably a wrong reference because it's probably from last semester, and I don't keep the numbers and the problems the same. So be careful about that one. I'll look if I remember and take it out if it's not. But propagation delay will tell you it's based solely on one thing: the length of the connection. That's it. Not the technology, not the bandwidth. It's considered to be a single length. So if I give you a problem, and the problem says, here's how long link A is, and you have some delay. And then here's how long B is, and you have some more delay. And here's how long C is, and you end up with a router, with another host at the end. And I tell you how long this one is, how long this one is, and how long this one is. It doesn't matter to your bit, the sequence of these that it goes over. It's going to have to go over all 3. So if you want to figure out the propagation delay, why not just add the 3 links together and then divide it by the 2.5 times 10 to the 8th and just do it once instead of having to do it 3 times. The same thing, router delay. If I tell you the first router subjects each packet to 4 milliseconds of a queuing delay, and on average, in the other one, it's 10 milliseconds of queuing delay, I'd say, okay, 14. Just add them together. And then I tell you processing delay is 2 milliseconds on each one, so that's another 4, so 18. So each packet is going to have 18 milliseconds of delay plus however much delay is on the propagation. It does not matter how you combine these. It's just math. And we know from associativity rules, A plus B plus C is the same thing as B plus A plus C and C plus B, so it doesn't make any difference. So don't freak out when you are asked maybe to calculate that. It's a whole lot simpler than it sounds at first. We saw lots of diagrams on them. Time goes down the page. So I'm talking about diagrams that look like this, like the one on this page here, right? So they're always going to go down the page. So if I ask you, if you believe it takes time for something to happen, boy, your line better have an angle to it. If you think something happens instantaneously, then it's horizontal. Also, the line should usually be symmetric. So whatever angle this is should match whatever angle this is. It should usually not take any longer to go in one direction than it does the other. That's not a guarantee. It's just unusual for it to do something different. So if I ask you to show me something or ask you what's going on, just remember that simple rule. Okay, there's a Wireshark PCAP file in the exam helper folder. So what I'm going to do now is share my screen. And let's see if I can go over to this folder and open this up. So I'm going to double click on it, and it's going to open it up in Wireshark. There are other PCAP files out there, PCAP readers out there on the internet. This part down here is usually not important, so I'm going to hide it. Let me see if I can find one for you guys. PCAP, let's see, PCAP sample. Let me try PCAP decoder. Here we go, PCAP total. Oh, I found it. It's the second link, not this one. So, all right, well, let's see what happens with this one. This one claims to be able to do it as well. So I'm just going to drag this on here and see what it shows me. I'm not a robot. Hopefully it believes me. Okay, here's analyze. Yeah, this is beginning to look like a phishing site to me. Yeah, so we're done with that one. Let's go back and find PCAP decoder. And this site at gasme.net, this one works. So if I want to drag this one over, so these are alternatives if you just can't get Wireshark to work. So, here it is. It's telling you what the packets are, what they do. It lets you drill down in them exactly the way Wireshark does, but it runs on a browser. So you can do this on your tablet or on your phone if you need to, if you're trying to glance at stuff. So I'm giving you the packet is the one you will have on the exam. I will give you the packet right now. Spend some time going over it. The things I want you to notice are how do they organize the layers? How do they, where do they sort information out? If I'm looking for information on an application, if I ask you a question about what application or something like that, you should know immediately where to go in the trace where all the application layer data is. If I ask you something about a layer 2 question, you should immediately go to the part of the trace that deals with layer 2, for example. And I will have these two packets, which is all that's in this PCAP. I will have these two packets inside, printed out as text in the exam for you as well. So in the case that you don't have if you don't want to print those out, they'll be in there for you. So this is what it looks like in Wireshark, and you saw what it looks like in some of the other ones. Okay. You may have a problem from the transmission versus propagation delay website. So if I go to that one, there it is, versus propagation delay. I should have kept sharing. So let me share this again. And what I'm thinking I'm going to do is show you a pair of diagrams. Okay, that's a little too fast. So I may be able to start, grab a snapshot, let's say right here, and then I may show you another one that's looks like this. Right, let's see how fast, right there. And then I'll ask you a question to say, can you tell by looking at these two diagrams if the length is longer than of one than the other, if the rate is different of one than the other, if the packet size is different than one and the other. And if you've played around with it at all and thought about it for a few minutes and you know what it means, for example, what the difference is between a packet entirely fitting on the wire and has space on either side versus the first part of the packet already making it all the way to the other end, and you haven't seen the end of the packet yet. So it's big enough at least to fill the whole thing. And I told you it was the same packet in both of these snapshots. What could explain the difference in behavior? You would consider things like, well, this network could be just a whole lot shorter. So I could have moved this up to the point and moved this up to where the packet is now on the whole network. Or I could give you a choice that says the packet got a lot larger. It's the same network, the packet just is huger. Or I could give you some other variable like that. So it'll be something straightforward like that, and I'll probably give you A, B, A, C, A, B choices, and you'll have to pick which one of them are possible. So it's not intended to be hard. Be prepared for another question like number 5 on homework 1. How long does it take a packet to propagate over a certain distance with this particular propagation speed? This speed that I show here is always the speed of every network, whether it's fiber, radio, Ethernet, whatever it might be. So if I neglect to tell you the speed on an exam, you should always assume for modeling that this is the correct speed, 2.5 times 10 to the 8th meters a second. So if I give you one like this, just be able to calculate what it is. It's a gimme. It's a simple question, but if you've not done it, it may be tough for you. Study problem number 8 on homework 1 and be able to tell me how long it takes to send a packet of link bell over a certain number of links where all the transmission rates are, let's say, the same, for example. We'll have another car caravan question, and this is the one that says your caravan has this many cars, it arrives at a toll booth, it takes this many seconds to process each vehicle, then they travel at this many kilometers per hour for this amount of distance until they reach the next toll booth. And I'll come up with an example and then ask you a question about it. And the question's probably going to be, does the first car arrive at the second toll booth before the first toll booth is done processing the vehicles? It'll be something like that. But I may ask you, how long does this road need to be so that the first car arrives at the second toll booth right as the last car leaves the first toll booth? So you'll have to figure out 10 cars, 5 seconds of processing a piece, that's 50 seconds of time. So if they're traveling at 100 kilometers per hour, how far can they go in 50 seconds? Not with seconds and kilometers, mind you. It'd be meters or something, but I'll make it car nice, like kilometers per hour and kilometers long. So you'll have to be able to do that up and down. Just have the equation, jot it down on here, be clear on what your variables are, and you're not going to have any issue. Okay, be able to calculate the total end-to-end delay for a packet that's running with a certain number of routers. They call them packet switches in the book, but they're routers. So routers have processing delay and queuing delay. Packet switches are transparent. Remember, we said that several times. They're transparent, which means they're invisible to us. We don't see hardware addresses. We don't see delay from them. The only thing they'll do is filter off data that they know is irrelevant to a link to reduce collisions. But we don't ever notice that. I mean, if somebody stopped someone from throwing a pie at you and you're just walking down the street, how would you even know? I mean, that's something that normally would be transparent. So having a packet come flying at you for a collision. So this one is basically asking you to calculate the end-to-end delay, where you DI, SI, and RI denote the length, propagation speed, and transmission rate for a link. So it'll be for a small number I, an integer less than 5, probably 2 or 3 nodes is all. And this is basically problem number 11 from homework 1. So the solutions are out there. Jot down the equation, run through it one time, and you should be okay. Remember the question that says, consider sending a file of this big from host A to B as one long message. What's the maximum number of bits that will be in the link at any given time? And it was part B of question 16. And of course, there's data missing in the sample problem, but go to question 16 and you'll see. But the question I want to ask is basically this one. So I want you to, it's a variation on the animation that we saw a minute ago, right? So it's basically saying, what's going to take longer, transmission delay or propagation delay? That's essentially the question. So if it's 800,000 bits and you're putting them on there, how long before the first bit reaches the other end? And in that amount of time, based on 2.5 times 10 to the 8th meters per second, that it takes for that first bit to reach the other end, how many bits could you transmit in that same amount of time? And is your packet larger or smaller than that number? So if you say, okay, 1,000-kilometer network, a bit travels at this speed, it's going to take 40 milliseconds for, and that's not accurate, but it's going to take 40 milliseconds for this first bit, once I get it on the wire, to make its way to the other end. 40 milliseconds, that's a long time. What's the bandwidth of my network? How many bits per second can I send? Is it 1,000 bits a second? Okay. How many bits can I send in 40 milliseconds? 40 thousandths of a second. And then look at your packet size. And let's say that comes out to be, I could send 400 bits in that amount of time. Okay. Is my packet bigger or smaller than 400 bits? So that's basically what you, with 2 or 3 of these questions, and what is likely to happen is I write this thing, I will combine several of these into one. You're not going to have 15 questions on the exam. You're probably going to have 7, 8, something like that. So I will collapse some of these together if I feel like maybe, let's say, if I can find a way to put this into the caravan question, I will. So a way of asking this one in the caravan question would be to say, okay, how many cars could fit on the toll road at the same time so that just as the first car arrives at the second toll booth, the last one has just left the first one? That's the same question. How many bits can you have on your network at the same time? So those are fundamental measurements of network efficiency that you need to learn. And so these are kind of all 3 or 4 of these have been variations on the same theme. Okay, HTTP exchange is a complete change of pace. So let me pull that one up. Delay estimation, and then go back to sharing again. So I gave a question like this in the spring as well, but so it'll be the same kind of question. It'll just change only in terms of the variables and the exact details. But you need to be able to either draw. Let me get my marker going here. You need to either be able to draw a diagram like this, finish a diagram like this, or identify a diagram like this. So if I ask you to identify this network or this drawing, and I told you there were 4 objects on this web page, and I want you to tell me if it's persistent or not, and then I want you to tell me if there's parallel connections, if it's not persistent, or pipelining if there is. Parallel and pipelining are the same thing as far as we're concerned, and they will be on the exam as well. If you answer parallel and you meant pipelining, it's a correct answer in my grade book. So if I ask you, first of all, is it persistent or not, you'd say no, because there's another TCP connection after the first one required to get the objects. Okay, cool. If I ask you to draw me what a one-object web page would look like with a persistent connection, you would draw a TCP, you would draw HTML, and then you would draw the object. But you would skip this because it's persistent. Or if I ask you, is this diagram correct for persistent connection? If it's got something that it shouldn't have, or if it's missing something, show me. And you would come in and go, well, it's not supposed to have this. So you just scratch through that, just like that, right? Or you'll say, remove second TCP round trip. If I ask you to tell me how many total round trips it is, make sure you understand how they calculate. So it'll be something simple. It'll be 5-minute type of problem. And it won't be as hard as the homework. It'll be easier. I just want to make sure you grasp that concept. So that one should be that one should be fun, I think. I think people did really well on it last semester. Okay, as promised, you will have a problem based on number 5 from homework 2, which began at, here's the DNS and HTTP delay interactive exercise. Be able to solve the following problem and answer the questions below. So if I go to the DNS HTTP website, and one reason why I'm using a lot of these diagrams is because it's really easy for you to go and practice a lot of times, and that's important to me. So let me see where I can't get the link. I've lost the link. Here we go. Nope, not that one. Let's see. Here it is right here. Okay, now I'm going to go share it. Share again. So that's what basically this one looked like. So I'm not going to ask you one that's this entire thing. I'm going to ask you that's something that is more general, more conceptual, and it'll be things like, how do web caches help? Here's an example of something. Does it make sense that a web cache would be useful in this type of situation or not? Do go through and make sure you understand kind of the math. This would be one that's sort of worthwhile. I'm very apprehensive about this problem, I will tell you, because I'm very nervous that this is too much. So if I get this tuned up, I will change the study guide. This is one where I need to give you some more detail. Now, if you sailed through this in the homework and you nailed it, great, you're set for whatever comes your way. But I'm nervous that it's longer, and I've done the old type of DNS problem I've asked for too many semesters, and it's just time for something completely different. So practice a few of these, but put them closer to the end of your list, because it's you'll be over practicing if you go through this thing hardcore 10 times, because I'm not going to give you the whole thing to try to deal with. I'm not sure if it'll even make the cut. So this is one to kind of keep an eye on Sunday. All right, from homework number 8, the TCP estimate simulator, be able to solve the same types of problems. So this is exactly the problem you're going to get. I mean, letter for letter, except this is going to have a number, and these are going to have numbers, and these are going to have numbers. So you'll need a calculator, but you're going to need to know how to fill these in just like you did on homework 4. So you can go directly to this website and practice, and it's basically the same thing. However, remember the email you got from Hassam. There were 2 bugs in the equations, and follow what he showed you in the equation. I drew the diagram for him that he included in that email. So make sure the most important thing you can do is write down the equations, and there are 3 of them you're going to need. They come right out of the book. If you search in the PDF file for estimated RTT, I think the very first time it's mentioned in the book is the very page where the first equation is. You go to the next page, it's got the equation for this. And you scroll down a little bit, and it's got the equation for TCP timeout value, which is not what the book calls it, but it is what this simulator calls it. So you're going to get a question on this one. And then to kind of wrap things up here, I'll have a transmission diagram for you like we did on problem 9 and homework 4. And it's extremely unhelpful that I tell you that without showing you which one that is. So let me pull it up. Problem 9 on homework 4A. All right, let's see if I can get it here. All right, I think what I want to do is pull one up actually on the simulator, because that's probably going to be a little easier to zoom in on. Okay, the simulator wastes a lot of space, and it also has kind of a glitch in it as well. So just like the email from Hassam that highlights for you the two places where they copy a number down where they weren't supposed to. The answers are still there in that other estimated RTT problem, but you've got to make sure if you're going to practice with that tool that you understand what those two changes are, so you don't get fooled. Similarly, on this tool, there's a problem sometimes that crops up in what they set the threshold to. So make sure you read the homework problem. It's got two little small pictures where I've taken snapshots, and it explains to you exactly what's going on. So let's walk through one of these together and make sure we kind of understand what's going on. Always, and this is really small, but there's a little red hyphen here, the SS threshold is going to be set at some value. You have to be told what the initial value is. You can't solve this problem unless you know what it is. So in this case, they gave us this tiny little red hyphen, which makes me like, well, thank you very little. But that is the point. Whenever you cross SS threshold, it's a variable, and whenever the size of your window crosses that value, you stop growing exponentially. Right? You will finish the round that you're in, perhaps, but you'll stop growing exponentially. So when I see what's happening here, I know that SS threshold is at this point, even if I didn't see the little red hyphen, because I stopped growing exponentially. And instead, I started growing linearly. So let's say this is 8 packets. That's what size my congestion window is. In the finite state machine that we went over in detail in lecture that's in the book, it tells you that when you are in slow start, every time you get an ACK, it basically means you're supposed to increase your collision window by 1 MSS. Well, you can't do that unless you're told what MSS is. What that means to most of us, though, is you grow by 1 packet. But once you hit threshold, once you hit the SS threshold, the way you grow linearly is by growing instead by MSS over the original congestion window. So you're going to grow by, if this was 8, then you're going to end up growing by 1/8 each time. And that makes sense. I'm at the point where my congestion window is set to the value of 8 right here, and I send out 8 packets, and I'm going to get 8 ACKs back. And what you're telling me is here, you want to end up at the end of this transmission round at 9. So the transmission round does not mean send 1 packet. The transmission round means send the entire window in 1 batch, as if it was just like 1 big packet. So that's what a transmission round is. You dump the contents of your full window. You always assume it's full. So you're going to get 8 acknowledgments back, and for each one of those acknowledgments, you're going to grow your window, but you're going to grow it from 8 to 9, or you're going to grow it from 16 to 17, or you're going to grow it from, if it was up here from 35 to 36, whatever it might be. And the only way you can do that is if each one of these ACKs overall is 1/nth a packet. All right, so that's the math behind it. So if I ask you, okay, show me what the value of congestion window is for each of the 8 acknowledgments you get between here and here, and I give you a table to fill out that says first acknowledgement, second acknowledgement, third acknowledgement, fourth acknowledgement, you're going to have to tell me, and the first one, it's 1 whatever it is. If it's at 8, you're going to have to tell me it's 1/8 larger, and here it's 2/8 larger, and here it's 3/8 larger, and here it's half of an MSS larger, half a packet larger. So that by the time you get down to 8, it's a whole packet larger. So I may ask you this to kind of help walk you through for yourself, but it'll be minimal points on that. It may even be some extra credit points or something. The goal of this exercise is to know what in the world's going on this diagram. So if I ask you, and we're going to use TCP Reno for everything exclusively, and I'll tell you if there's an exception. Otherwise, assume TCP Reno just like you're going to assume 2.5 times 10 to the 8 meters per second for propagation speed. So if I ask you, okay, what happened here? You're going to tell me two things. It was a loss. And I'm sorry, if I click twice, I get out of drawing mode, so that's why it looks like HOSS, but it's supposed to be an L there. You're going to tell me it's a loss. And if I ask you if it was a loss from a triple duplicate ACK or if it's a loss from a timeout, you should know this is a loss from a timeout. And if I ask you, can you tell from this diagram whether it's running TCP Reno or TCP Tahoe? The only difference between the two is the way they handle a triple duplicate ACK. And you don't see any evidence, I don't see any evidence on this particular diagram of somebody recovering from a loss by only dropping down to half. So there is no evidence that would convince me that it's one or the other, because I don't see it. If I come back up here to the top and I do it again, generate another problem like this one. Okay, this one's filthy. I'm not going to give you a nasty one. Okay, this one's decent. This one's decent. I know instantly it's TCP Reno because on the right-hand end over there, I see that there's a, I've got to switch my pen back here. I see that there's a loss. So what happened to my SS threshold? Well, in all these other cases, whatever value you're at, you drop your threshold to half. Please do not guess the number. Please be absolutely specific. If you can't tell whether this right here is at 16 or 17 or 18, just count. This one is at 15. It has a line going through it. This one's 16, this one's 17. Don't guess the number, figure it out. So this one is easy because it has a line going through it. It's 20. You're going to cut the threshold to 10, but your SS threshold, but you're going to set your window size to 1 because it was a timeout. Over here, if I move this out of the way, you were at what value? 21. And what's my threshold going to be set to? 21 divided by 2 equals 10.5. You have to round up for these, and there's good examples of why you should do one versus the other, and Hassam and I had a really interesting conversation about it. But I'm going to tell you to round up. If you mess it up and round down, we're going to count it right because it's not something this tool teaches you. The book doesn't teach you. We didn't really focus on it very much. So just know that you can't have 10.5. Pick a number. Pick 10 or 11. I would suggest rounding up. Okay, then it makes more sense for base cases that we're not going to bother with right now. So let's say it goes to 11. All right, so here's 11. Oh, I double-clicked. See, I did it. I draw it here. So I'm going to set my threshold to 11. And, of course, it picks yellow. It's going to be at 11, so it's going to be your SS threshold. What about your congestion window? Well, your congestion window is normally set to the same value, but in triple duplicate ACK, because you sent 3 packets after the one that was lost, then we're going to give you credit for those 3. So this is what was explained in the homework problem. You're going to add 3. It's also what's printed in the finite state machine that we spent a lot of time going over in lecture. It's also what's in the book when it says you've entered, fast recovery, basically. Okay, so I'll ask you a few questions like that. Of course, these all, we haven't looked at it, but they all have solutions. I will draw an example that is not at all ambiguous. It will be clear if there's a value that you'll be able to tell what it is. I managed to build a tool that actually drew a line across for each number, so you didn't have to guess where something was. It didn't waste any time, and the numbers at the bottom lined up perfectly with the columns, which this doesn't do any of those 3 things. So I've improved on the diagram. You'll get you'll get one of these. So practice that one. And then I'm considering a question from the selective repeat animation tool. And if I can find it here. All right. So what that one would be a fun one. Make sure you know what selective repeat does. So this is one where it is not TCP Reno, but it has a window on both sides. So if I show you, and I then go something like this, and I pause it, and I axe this one and ask you then what's going to happen when this arrives. Or if I show you one that, like the book did, where they had some that were already acknowledged here and they weren't yet acknowledged up here, and ask you what's gonna happen. Play around with it a little bit and work your way through the questions of what's the normal behavior when 0 and 2 arrive. How many more packets am I going to be able to immediately send? Is my window going to move when 0 arrives? Yes, it will. 0 you'll be done with. The window will move over 1. It's looking for the ACK from 1. When 2 arrives, it'll say thank you, but it will not move the window over, right? So it moved it over here, but when this one arrives, it doesn't, because it's waiting on the ACK for 1. So what will happen when 3 and 4 arrive? They'll arrive fine. Can I send another packet? Yeah, you can send it anytime you want. But that's the last one you're going to be able to send. And so if I give you a series of events, you send 4 packets. The first one is lost, or the second packet is lost. And I'll try to make the numbers the same, so you start numbering with 1, so you're not trying to figure out, did he mean the packet numbered 1 or did he mean the first packet? So we'll try to make the numbers kind of match. And I give you kind of several things here, and I ask you to sort of draw me where the window is going to be, or which of the following descriptions matches this image. I'm trying to find one that will be easy enough for you. So the exam is 1 hour, and we will continue on with lecture afterward. And so it doesn't make any sense to do the lecture first, because everybody's a nervous wreck and nobody's paying attention, and I don't want to teach you new information right before I give you an exam. So we'll start the day off with an exam at 8. You can come whenever you want, but it ends at 9. And we'll have an hour of lecture at that point. If you nail this thing in 15 minutes and you look at your watch and you're like, I can make it back to the coffee shop and listen to the next hour on WebEx, knock yourself out. You're welcome to do that. Okay, let's see here. I want to share the homework problem. And I think all the questions I had were on problem number 5, if I can find it here. Okay, so this problem threw a lot of people for a loop. So what I want to do, since when I zoom in on this, which I've just now done on my screen, it doesn't zoom it in for anybody else, and it desperately needs to be zoomed in. What I'm going to do is take a snapshot of this thing right here and switch to that drawing tool that I like. So we're going to go over to Sketchbook. And I'm going to paste this in. Okay, so move this around. This looks okay. So I'll pick my drawing tool and let's talk about this for a minute. So if this packet is lost, the next packet that arrives isn't going to be the normal acknowledgement for this packet, because the receiver wasn't expecting that one next. It was expecting this one next. So when did you first receive the information from the receiver that he was prepared to get this data? Well, he sent you an ACK back telling you, he's ready for this segment. So let's say this segment starts with sequence number 100, just for grins. and each one of the packets is 10 bytes long. So this would have been starting with 90, this would have been 80, this will be 110, 120, this, and if we don't have any retransmission stuff messing us up here, that's what these guys are going to be here. Okay, so I send 80, and an acknowledgement comes back for 90. I'm ready for 90. I send 90, I get an acknowledgement back for the next one after the end of that packet, which will be 100. I get the next packet, which is 110 through 119. What ACK am I going to get here? Am I going to get 120? No. You're still waiting on 100. So you're going to send it the ACK again. And when this packet shows up, so my window size was obviously 5. I dumped 5 packets out all at once. I got an acknowledgement back for every single one of them. And that's the way we'll do it, one by one. I'm going to get the same ACK back again. I now have 2 duplicates. As soon as I get a triple duplicate, then I'm going to resend packet at time 3. This one with sequence number 100, let's say. So what's going on here? Why am I sending 2 more packets, and are they the retransmission? No, you can send 5 packets. The animation that we just looked at showed you when the first 2 acknowledgments come by, you move your window on down, and you'll move your window down to here. And so you have room for 2 more packets, and there they are, right here. They get sent at time t equals 15 and 16 because you have to wait until you receive these 2 ACKs to move your window and then send it. So this one was sent at time 1. It arrived at time 8. So there's obviously 7 time units of delay between 1 and 8. And then 8 to 15 is another 7. Same amount of delay in each direction. When I send this one out, when's it going to arrive over here? And what's it going to do? Is it going to acknowledge that it received 130? Or is it going to do something else? And then when is that something else, or the ACK for 130, when is it going to arrive? At what time? So what I can tell you is the retransmission will not happen on this sheet of paper. It happens off the bottom of the page. So if you think it's going to happen here, or here, or here, you got it wrong. You need to figure out and just meticulously decide, if I'm going to send a packet and I'm going to start it, if this is my problem here, then this one doesn't make it. When is this acknowledgement? +7 here, +7 there. That allows me to send another one. +7 here, +7 here. So as soon as I get this one, I start sending another one. What's he going to send back? So just add the time to each one of them. All right, so that was one of the questions that I was asked to go over. The other one is 5C. So let me get back to this. And so 5C is just basically documenting what you've learned. Right? So if you know that if we start at a certain sequence number, and maybe I gave you a sequence number, I think I did. Each segment is 150 bytes. The initial value of the sequence number is 100. Okay, so this will be sequence 100, and it will contain packets 100 through 149. That's 150 packets. So the receiver is going to acknowledge the next packet he expects. So this one is going to have sequence number 150, and so on. We're going to continue on like that. All right, and what you got to figure out is time 1, 2, 3, 4, 5, 15, 16, 18, 19. So if I go here and look at the thing, 15, 16, 18, 19, does this make sense? Does this make sense? Do these make sense? Are these really going to be sent? The rule is you will not move your window over past the oldest unacknowledged ACK. So I have 1, 2, 3, 4, 5, 6, 7, 8 packet numbers, and I have my window is initially here. When I get an acknowledgement back for this guy, my window slides over. I will not slide the window any further until I get an acknowledgement back for this packet. And the acknowledgement number will be the starting sequence number of this. Remember, you acknowledge the next one that you expect to receive. When I receive the acknowledgement with this value or any other higher value, I know they must have received packet 2. So if you know this rule, and you ought to be burned in by now, then you should be able to spot a really big problem with this diagram. What they've shown is impossible. And so that's a big hint on part C. So if you think you filled out every one of these times and filled out the sequence numbers, you got fooled. So you need to go back and pay very close attention. If you're not sure, run this in the simulator. Go back to the simulator, send 5 packets, kill off packet number 3, and see what happens. See what happens. And see if it will let you send 2 more. Will it let you send 4 more? Does it actually send these acknowledgments back? So you can play with it in the simulator. That's why you have that tool. It'll tell you what's wrong with this diagram. So you may have one, similar to this, but I'll tell you it's very, very similar to the animation. So anything I think I would ask you here would probably be packed in that animation. I may ask you to draw something, like this, for example, but it'd be simple if I did. I might give you the base of it and say, okay, show me where the window is at time, something like that. So it's all based on the window. It's really, really key you understand when the window moves and when it moves, how far it moves. Okay? All right, guys, that's all I had for you on this today. We'll continue on. We all leave now. For those of you who haven't been on a single live broadcast, we all go away at this point. Hassam comes on, and he'll answer any questions we have normally, but because this one's just a midterm review, and it's a Friday, he doesn't come on Fridays. They get Friday. That's the one day they get off. So if you want to ask him a question about something, a really good way to start the conversation would be, I was on the prof's lecture on Friday evening, but I still have a question about 5C, as opposed to asking something that we just covered in the exam or in the last hour that you just didn't know about, or like, can we bring a piece of paper to the exam, stuff like that. So that's a bad way to start off a conversation with those guys. And one of them's usually in a little better mood about that than the other. But the other one will basically tell you, why don't you listen to the lectures before you bother me? And I had one TA one time who's actually the most productive TA he's right up there with the best ones. And I mean, he would scold you for doing it. I don't think these guys will do that, but just stay on their good side. They have a lot of control over giving you extensions. That's up to them, right? So they can be your best friend if you're trying to juggle a couple of things. So I'll see you guys on Monday morning, and then what I'm going to do, since Hassam isn't here, is we will really all leave at this point, and then I'll record the second hour and upload it to YouTube a little later. It takes about 30 to 40 minutes, it seems, much longer than it did in days past, probably because I have a different license. So this recording that we just finished will not be available probably for an hour, I would guess. If you don't see it by then and you're looking for it, ping me. All right, guys, I will be in Houston on Saturday and Sunday most of the day, but I'll be terribly jet lagged, so text me, but I may be trying to catch up on a little bit of sleep. Bye, everyone. Hope you guys have a great weekend. So long.